Thank you on behalf of myself and the collaboration for this kind invitation. I'm sorry I couldn't be there in person. The Gamma Ray Astronomy at PEV Energy's Phase 3 collaboration consists of researchers from 7 institutes in Japan and 14 in India, all led by the Tata Institute of Fundamental Research in Mumbai. The collaboration operates an air shower array at an altitude of 2,200 meters in the Nilgiri Mountains in South India at these coordinates. And the air shower array consists of two main detection elements. There is a scintillator array, which you see here, made up of these pyramidal modules. And then there is the GRAPES-3 muon telescope, which are these 4 buildings you see here. The scintillator array consists of 400 such pyramidal detectors, each having a 1 meter square area plate of plastic scintillators with nanosecond relaxation time. There are a majority of the detectors are of the fiber type, while a few are of the cone type. In the cone type, the PMT looks downwards at 5 centimeter thick scintillator tiles. And in the fiber type, the optical coupling between the scintillators and the PMTs is achieved using wavelength shifting fibers. Because of the higher efficiency in transferring photons in the fiber type, we use only 2 centimeter thick scintillators in the fiber type detectors. Here you will not see the difference between the two types of detectors because these pyramidal casings are used for both. In some of the fiber type detectors, we have 2 separate PMTs with different number of wavelength shifting fibers going in so that they operate at different gain levels to enable a higher dynamic range. The modules are separated by 8 meters and they cover an area of 25,000 meters square. So with an 8-meter separation, this is the lowest energy threshold detector of this scale in the world. And the scintillator array sees about 40 hertz of trigger rate, meaning it is able to record about 3 million extensive air showers in the energy range of 1 TeV to 10 PeV per day. Now, the waveforms from the PMTs of these detectors are digitized using analog to digital converter circuits and time to digital converter circuits. The ADC output, along with calibration information, can be used to infer the distribution of number of particles within the detector array, so within each of the modules of the array. And that information can then be used to reconstruct the core of the extensive air shower. That data can be fit with the Nishimura-Kumata-Grayson function to give you the age and the size of the shower, which the size of the shower given a specific primary species is then a good proxy for the energy. The timing information from the TDCs can be used to estimate the direction of the primary particle by fitting a plane to the shower front. In particular, the observed age and size dependent curvature or change in slope of the shower plane has been implemented as corrections. And this has allowed GRAPES-3 to have an angular resolution of almost 0.2 degrees at when it is approaching a PeV in energy, making it the best angular resolution at those energies. The GRAPES-3 muon telescope consists of 16 modules. So each of these buildings you see is a station, and the station itself consists of four modules. And it is made up of gas-based detectors called proportional counters, which are steel tubes with a tungsten anode going through the center, which are 10 centimeter by 10 centimeter by 6 meters in dimension. They are hermetically sealed and filled with P10 gas, which is made up of 90% argon and 10% methane. And when a charged particle goes through, you get a Townsend avalanche. And if that is, if you have a very high voltage applied between the cathode and the anode, and the pulse you can read out, and you can detect the particle traversing, passing through these proportional counters with microsecond resolution. So the combined area of these four detect muon stations is about 560 meters square. They consist of 4 layers of these proportional counters, and in each layer, the counters are perpendicular to each other, meaning alternate layers can be used to reconstruct the direction of the muons in along two different coordinates. And there is an absorber of 2-meter thickness, providing a grammage of 550 grams per centimeter square, and making sure that only muons of energy at least 1 GeV in the vertical direction will penetrate the absorber and reach the proportional counter layers. So data from the muon telescope is read out in 2 modes. The number of coincidences among all 4 layers leads to a muon being detected, and then its direction is reconstructed, and the number of muons in each of these directional bins is binned in 10-second time bins, and you get that as data. In addition, this is called the angular flux data, and in addition, the number of muon tracks within the detector and all associated hits are also read out whenever an external trigger is received from the scintillator array. So this shows a schematic of the layout of the detector. The blue squares correspond to the scintillator detector modules, and the green squares correspond to each of the module of the muon telescope, with the 4 squares corresponding to the stations. So compared to all other air shower arrays in the world, GRAPES-3 has the lowest latitude in the northern hemisphere, and as a result, it can nicely complement the detectors in the southern hemisphere and the detector together with the detectors in the northern hemisphere from a point of view of latitude-dependent systematics. So the GRAPES-3 scintillator array was constructed, finished construction in 2013, while the muon telescope was, finished construction in 2000. And over the past decade, GRAPES-3 has produced very exciting results that is, using data from the muon telescope in the domains of atmospheric and solar and heliospheric physics. And by using data from the scintillator array and also the muon telescope combined in the last 3 years, we have been also able to produce some interesting results in cosmic ray physics. I myself joined the collaboration only in 2021, but for completeness, I will briefly flash through all the highlight results from GRAPES-3, even from the past. However, the solar and heliospheric highlight results and atmospheric highlight results, etc., have also been covered in detail in the 2022 ISWECRI by Dr. Hariharan. So I will be quick when going through that. So on 1st December 2014, for a period that lasted almost 18 minutes, the GRAPES-3 muon telescopes along different directions saw the muon flux change by almost 1.5%. And this was interpreted to be due to the acceleration of atmospheric muons in a thundercloud. And the basic idea is that mu plus will get accelerated while mu minus will get decelerated. But since the mu plus by mu minus ratio in atmospheric muons is greater than 1, this should lead to a reduction in the total number of muons you see within the detector. This change in the muon flux also coincided with the observed changes in the electric fields reported by electric field monitors operated near GRAPES-3. And over a period of 18 minutes, this change in the muon flux traveled across the different directions of the GRAPES-3 detector, allowing the movement of the cloud to be tracked with a precision of, it was found to move at a rate of 6.2 degrees per minute. And by comparing the level of reduction in the muon flux with simulations, the potential in the thundercloud could be inferred, and it was found to be about 1.3 gigavolts. The systematics uncertainties on this from considerations of the hadronic interaction model, from uncertainties in the mu plus over mu minus ratio, etc., have been quantified in a latter paper, but the initial result was published in this paper in PRL. And this then confirms a prediction that was made almost 90 years ago by the Nobel laureate Wilson. And more recently, by studying the rate of particle densities in the scintillator detectors, both cone and fiber type detectors, over the last decade, we have been able to observe correlations at high statistical significance with both the temperature and the pressure operated at site, obtained from temperature and pressure monitors operated at site by the collaboration. And we're in the process of figuring out how to implement these for corrections to better calibrate our detector. In the domain of solar and heliospheric physics, GRAPES-3 produced some very interesting results which were published in PRL in 2016, wherein for a period of 1 hour or so on 22nd June 2015, the muon telescopes in their flux of muons reported in all directions summed together demonstrated a deviation of more than 50 standard deviations. This was then interpreted to be due to the transient weakening of the Earth's magnetic shield due to a solar storm, because the different directions of the GRAPES-3 muon telescope correspond to different cutoff rigidities, and simulations for the solar storm, taking into account the different cutoff rigidities, are able to closely match the actual increase in the muon flux as observed. And also it coincided with a reduction in the interplanetary magnetic field at L1. This marks out GRAPES-3 as, especially the GRAPES-3 muon telescope, as an extremely sensitive instrument that is capable of detecting changes in the interplanetary magnetic field at the level of a few nanotesla. The more recent update is that a similar change in the rate at that exact period has also been observed from the scintillator detectors. This brings me to the most recent results in the domain of cosmic ray physics. The improved angular resolution of GRAPES-3 and pointing due to the shower front curvature corrections that I mentioned earlier on a slide, we have been able to validate it over 3 years of data by observing and characterizing the shadow of the moon. And the width of the shadow of the moon in samples of different energy thresholds is shown here. And by fitting for this in a Heel-Pix map, we were able to quantify the GRAPES-3 pointing to be better than about 0.03 degrees and 0.09 degrees in the right ascension and declination directions. And our earlier claim that the angular resolution approaches close to 0.2 degrees at the highest of energies stands validated in its absolute pointing. You may be aware that detectors such as Hawk and Argo YBJ, especially also in the talk which was there today, have been able to observe small-scale anisotropies in the arrival directions of cosmic rays. We have also confirmed the existence of these anisotropic structures in our data, which was published in this paper recently. We started with a sample of almost 4 billion events from the scintillator array in a period between 1st January 2013 and 31st December 2016, corresponding to about 4 years of lifetime. This sample has a median energy of about 16 TeV. And once you make a sky map of that sample and you compare it against a time scrambled sky map, you see clearly two regions which correspond to also or overlap with at least regions also reported by Hawk, which we are calling region A and region B. And using the method of Lee and Ma, the statistical significance of region A was found to be 6.8 sigma, and the statistical significance of region B was found to be 4.7 sigma. The background, these two regions can actually be seen very clearly from this plot as the deviation in the signal plus background when you compare with the background only as obtained from time scrambling. And the relative intensity of the two regions in their detail without smoothing are shown here. The intensity of these two regions, the peak intensity as observed by GRAPES-3, is very much compatible with what has been reported by Hawk and Argo YBJ. And the morphologies are slightly different, but we are in the process of doing a multi-detector analysis with Hawk. We are in early stages of discussion to combine our data with both Hawk and IceTop to understand the systematics in this better. We have done the same analysis using the anti-sidereal time and the extended sidereal time, and the resultant maps do not show any such features as the A and B structures we saw in our maps. This gives us reasonable confidence that this is not some kind of spurious sidereal effect. The fact that GRAPES-3 has a muon telescope operating at the same site as the scintillator array allows us to also test if these anisotropies could be due to high energy gamma rays. And what we did was we basically rejected any of the the scintillator array events which did not have at least two tracks within the muon detector. With simulations, we have determined that this allows us to reject 98% of the gamma rays. If we had insisted on having only at least one track in the muon detector, it would have been 89%. So we are left with roughly half the events we started out with after we apply this cut. But the intensity of the region within the maps changes by less than 1 sigma. This leads us to believe that the primary contribution to these structures is hadronic and it is not from gamma rays. By using data from the scintillator array and the muon telescope together, we have also been able to measure the spectrum of protons in the energy range where GRAPES-3 is sensitive. So we started out with about 1.8 billion EAS triggered events over a period of 460 days between 1st January 2014 and 26 October 2015. However, we did not want to consider misreconstructed events which may fall near the edge of the detector. So only events within 50 meters of the center of the scintillator array were considered. More importantly, to be able to tell the protons apart from other primaries, the number of muons we see within the muon telescope is important. However, we had to reduce we had to make sure that is not contaminated by hadron punch through. So we had to make only select showers which fell at least 60 meters away from the muon telescope. This means that we had a fiducial area which was given by this crescent-shaped pink region. And by also additionally applying cuts on the inclination angle, by selecting only events that have a large enough size to have trigger efficiency about 90%, and having only event ages from the NKG fit, which are well reconstructed. We reduced the sample by almost two orders of magnitude to about 8 million over the same period. And then we used Gold's unfolding algorithm to extract the relative composition of protons and also the flux of protons over this energy range. And once we factor in all the systematic uncertainties arising from both statistics in the unfolding algorithm as well as uncertainties in detector acceptance and relative composition, etc., as well as biases and uncertainties due to limited Monte Carlo statistics, we have a systematic uncertainty of the order of 10%, plus or minus 10% on the flux in each bin. And when we fitted a broken power law to the data points in each bin, we found that it was favored over an unbroken power law at more than 3.2 sigma statistical significance, with the break being at 166 TeV. This is for the first time, this has been reported directly from data. It was hinted at by Paolo Lipari and Bernetto in this paper from 2020, where they compare measurements from direct experiments to measurements from indirect air shower array data points from indirect air shower array measurements. And they said that such a break is to be expected if the indirect measurements based on Sybil 2.1 hadronic interaction model is believed to be reliable. This break at around 166 TeV. Interestingly, a very recent paper by Dampe, even though they have very little statistics at those energies, also report a hardening at around 150 TeV. And because it's a direct measurement, the absolute energy, there could be differences in the absolute energy calibration between air shower arrays and direct measurements. So in summary, we have detected a new feature in the cosmic ray spectrum, wherein at around 166 TeV, the cosmic ray spectrum hardens from a spectral index of minus 3.12 to about minus 2.56. And before I come to a conclusion, I will briefly show what Dr. Hariharan mentioned during the Hawk talk, which is that with the recent Tonga volcano eruption, the rates in both the scintillator detectors as well as the muon telescope show statistically significant variations that coincided with the pressure waves from the volcano eruption. And you can find more details about this in this ICRC proceeding. In the near future, the collaboration is hoping to finish construction of the new muon telescope, which, unlike the old muon telescope, so the old muon telescope consisted of 4 modules grouped into one station, and then 4 stations, which are 4 different buildings. In this case, all 16 modules together are in one civil construction. This is a construction that began in 2016 or so, but then had to be halted during the pandemic. And recently we have been able to restart this and complete most of the works. The work for putting in an absorber is soon about to begin. And the aim is that the absorber for the new muon telescope will enable muons down to inclinations of 60 degrees to be reconstructed, allowing 70% larger sky coverage for also for atmospheric and solar studies. In summary, the GRAPES-3 observatory has matured into an observatory that's capable of doing atmospheric and solar and heliospheric physics studies using data from the GRAPES-3 muon telescope, which has seen and confirmed the gigavolt potential in a thundercloud, as well as confirmed confirmed a short muon burst triggered by a transient weakening of the geomagnetic field. It has observed it, not confirmed it, sorry. GRAPES-3 has also been able to measure, for example, the cosmic ray parallel mean free path and rigidity dependence on solar activity. I have some backup slides on this. Curvature for the shower front, corrections for the shower front curvature have enabled the scintillator array to have an angular resolution approaching 0.2 degrees at the highest energies, and this has now been validated. The absolute pointing of the detector over 3 years of data has been validated with the moon shadow analysis. We have matured into an astroparticle physics observatory by observing and characterizing small-scale anisotropy at DeV energies in cosmic rays. The analysis for large-scale anisotropy is currently ongoing. By the way, the student who performed this analysis, Medha Chakrabarti, she led the analysis. She is now on the lookout for a postdoctoral position. So if anyone wants to, please feel free to reach out to her. GRAPES-3 has also, by combining data from the scintillator array and also the muon telescope, managed to identify a new feature in the proton spectrum, a hardening at about 166 TeV. The collaboration is now in the process of moving towards blinded analyses, and that is, we are slowly starting to do blinded analyses and also start using machine learning based reconstruction algorithms using graph neural networks. So in the near future, in the next year or two, or maybe by next ISWECRI, you will hear more about this. We are also working on the spectrum and composition of heavier elements, not just proton. We are currently seeing hints of the Crab Nebula in muon poor showers at close to 5 sigma in 9 years of data. However, we are still working on understanding our point spread function, but we have also started a search for gamma ray transients, and we are in the early stages of having a joint cosmic ray anisotropy analysis with IceCube and Hawk. With the new muon telescope being completed soon, we also hope to extend our scintillator array so that we can achieve a sensitivity of 10% of Crab within 1 year. We have put up the proposal for this recently, and we wait to see if we will be supported in that endeavor. So with that, I would like to conclude my talk. If anyone has any questions, I'd be happy.
Thanks a lot. Excellent. Thanks. Okay, it's very interesting to see also the structure now emerging from the knee with the different measurements. Let's see, comments or questions on the talk. I'm first looking here in the room. So let me ask you, the one thing is you mentioned that from the scintillators you have an ADC count of the charge. Do you have traces also that you can see?
Do we have what?
Do you have time traces for individual scintillator signals? So my question is, forgetting you have a TDC and you have an ADC that you showed in one of the early slides. And my question is, whether you see how the signal looks like that you have in the scintillator, the time resolved.
Okay. I do not have any slides right now where I can show that, but like I said, I joined the collaboration only in 2021, but Dr. Hariharan, who is connected, and also I think Professor Sunil Gupta, who's the leader of the collaboration, is there among the audience. So maybe they may be able to tell you more details of what you're asking.
Yeah, thanks, Ramesh. Basically, we only record the charge in the pulse. So we don't have any information about the shape of the pulse. But that, unfortunately, we are not recording. Yeah. It's a charge integrating ADC. So basically, you integrate, you charge a capacitor inside the ADC. It's an old-fashioned way of doing things.
Yeah. Then I know, but then I have also an interesting comment later at the conference. Okay, good. Oh, there's an online question. I don't know who it is, but please speak.
Reddy, I see your hand is raised. If you have a question, you can unmute yourself and ask now. That's
Yeah, so
both.
please speak. Oh, he's muting himself.
Dr.
Now-
Ramesh, can you hear me, please?
Yes, we hear you.
We can hear you, yes.
Dr. Ramesh,
Yes, we can hear you.
see, GRAPES-3 has a lot of potential regarding thunderstorm data and corona mass ejections, and apart from scintillator data and main angle data, we have large data for thunderstorm data. Whether we are concentrating on in analysis, and that is first question. Second question is, when our second Mayan telescope will be added into mainstream, how long it will take?
So I can say that recently we have expanded the collaboration significantly, and more researchers from high energy physics domain who are interested in our data have joined, and they have begun analysis, and more students are working on it. So from that point of view, all the data we are recording, the results, the speed at which it comes out, it should significantly improve. And also we are using better tools like GNN, etc. And your second question, the new Muon telescope, we expect to, well, the DAQ systems can be connected and we can start recording data within 1 to 2 years time. But I currently do not know what is the expected time frame for the absorber to be completed, because that's an additional civil construction. But I would say that maximum 2 years is what we are looking at.
2 more years, roughly. Thank you, Dr. Ramesh.
Yeah, we are looking forward to seeing the new data also to come. And it's very good that the array is going to continue to run, because many others are turned off actually. Yeah, I see another question. Carlos?
Thank you. Sorry, I missed what hadronic interaction model you used to reconstruct the proton spectrum you mentioned.
Sorry, the hadronic interaction model?
The hadronic interaction model that you used in order to reconstruct the proton spectrum.
Yeah, that's QGS2. It's QGS Jet 24.
Okay. That is because that comes for my next question. Have you compared the result with the hardening observed also by Hawk, which use also QGS204? That is because in Hawk we are using the shower age, and you are using here another observable. If you see differences in that, and if you see differences, what do you think could be the reason?
So the Hawk hardening is at a lower energy, right? It's not at the same place. If I remember correctly.
It is almost at the same place, but if I remember well, there were some differences in the intensity with the previous result that you had before. I don't know for this one.
I see. By intensity, you mean in the anisotropies? Or
No. With the magnitude of the energy spectrum.
Okay. You mean the normal, the flux?
Yes.
Yeah. So we are now in the process of doing the composition study for all species, not just proton, and also we are quantifying the systematics from different hadronic interaction models in a more careful way. So I hope to be able to do a more detailed comparison with what Hawk is doing, in the near future. Right now, I cannot comment. Sorry.
Okay, thanks a lot. We have to conclude here the discussion because we have to go to the next talk. Thanks again.